I was driving past this massive solar farm the other day, just row after row of those dark, sleek panels soaking up the sun. And it struck me how we've totally normalized what is, it's essentially quantum magic. You have a rock silicon sitting in the sun,
Mhm.
and because light hits it, invisible particles jump around and, power our coffee makers.
It really is magic that became mundane. We treat it like it's plumbing, but it's actually the direct application of quantum mechanics.
Exactly. And that technology, that entire industry, rests on a rule book written all the way back in 1905 by Albert Einstein, the photoelectric effect. But here is the thought experiment I want to run by you today. I want you to imagine a mirror world version of that solar farm.
A mirror world.
Yeah, imagine instead of normal silicon and copper wire, you're looking at a device made of antimatter. Instead of popping out nice, safe electrons to charge your phone, this thing is blasting out positrons. It's a completely alien concept, but according to the research we have in front of us today, it's not just sci-fi. It's a theoretical framework that is actually being built.
It is theoretically possible, though the engineering challenges are, well, nightmare might be too soft a word, but the physics. The physics is absolutely fascinating.
That is our mission for this deep dive. We are unpacking a really mind-bending paper by a researcher named Reza Kanga. The title is a bit of a mouthful. Extending the photoelectric effect to positrons. But essentially, we are going to see what happens when you take one of the oldest, most reliable laws of physics and try to rewrite it for the volatile, explosive world of antimatter.
And I think it's important to state right up front, this isn't just some creative writing exercise. This paper is addressing a legitimate gap in our understanding. We've had the rules for how light interacts with matter for over a century, but the rules for how light interacts with antimatter surfaces, that page of the textbook is surprisingly blank.
So to navigate this, let's set a roadmap. First, we need to do a quick refresh on what Einstein actually discovered in 1905 because, spoiler alert for you, it wasn't relativity that won him the Nobel Prize.
Right.
Then, we need to understand why standard physics has completely ignored antimatter in this equation until now.
And finally, we are going to deconstruct the new equation proposed in this paper. It takes Einstein's simple math and adds some really intense corrections for things like annihilation risk and symmetry breaking.
Annihilation risk is definitely a term that grabs your attention. So let's start with the history. 1905, the miracle year. Einstein is just cranking out papers. I feel like most people associate him with E equals mc squared.
Right. And while that's the equation on the T-shirts, it's not the one the Nobel Committee cared about at the time. Einstein won the Nobel for the photoelectric effect. And to understand why that was such a huge deal, you have to put yourself in the mindset of a physicist in, say, 1900.
Okay, so back then, everyone thought light was a wave, like ripples in a pond.
Exactly. And that intuition makes sense. You see light spread out, you see it bend around corners. But there was a problem. If light is just a wave, imagine you have a piece of metal. You shine a very dim light on it. According to the wave theory, that metal should slowly soak up the energy, like a sponge soaking up water. Eventually, the electrons inside should get enough energy to pop off the surface.
It's like heating a pot of water. Even a low flame will eventually make it boil if you wait long enough.
Precisely. That was the prediction. But when they did the experiments, that's not what happened. If the light was too dim specifically, if the frequency was too low, nothing happened. You could leave the light on for 1,000 years and not a single electron would pop off. But if you changed the color of the light, shifted it to blue or ultraviolet, boom, instant electrons.
It was instant or nothing. And that's where Einstein stepped in. And he broke the paradigm. He said, we're looking at this wrong. Light isn't just a wave.
He realized light comes in packets, discrete little bullets of energy. We call them photons. And this changed the math entirely. It became a collision problem. One photon hits one electron. It's like a game of pool.
Okay, so let's talk about the mechanics of that collision. In the notes, I see this term work function. It feels like this is the central concept we need to get our heads around before we can flip it to antimatter.
It is. Think of the work function as the cover charge to get out of a nightclub. The metal, the club, wants to keep the electron inside. It binds it with a specific amount of energy. That's the work function.
So the photon is the patron trying to pay for the electron's exit.
Exactly. If the incoming photon has enough energy to pay that cover charge, the electron gets kicked out. If the photon have even a penny less than the cover charge, the bouncer says no. The electron stays put. It doesn't matter if you send 1 million poor photons. They don't pool their money, It's a one-on-one transaction.
So Einstein gives us this beautiful, simple equation. The energy of the photon equals the kinetic energy of the escaping electron plus the work function. E equals k plus phi. It's elegant. It explains everything we see with solar panels and sensors today.
It is elegant, but here's the catch, and the reason we are doing this deep dive. That equation has a massive blind spot. It assumes the universe is made of only one type of stuff.
It assumes matter, electrons.
Right, and to be fair to Einstein, in 1905, nobody knew antimatter existed. The positron, the antimatter twin of the electron, wasn't even predicted until Paul Dirac came along in 1928, decades later.
Yeah.
So Einstein's equation is perfect for the world he knew, but it's incomplete if we want to describe the whole universe.
Okay, so let's bring the positron onto the stage. This is the mirror world part of the discussion. For anyone who hasn't thought about particle physics since high school, what exactly defines a positron?
A positron is the mirror image of an electron. It has the exact same mass, it has the same spin, but instead of a negative electrical charge, it has a positive charge, hence positron.
And the source material leans heavily on this concept of symmetry, specifically something called CPT invariance. I want to spend a minute here because this seems to be the philosophical bedrock of the paper.
It's the golden rule of modern physics. CPT stands for charge, parity, and time. The theory of quantum electrodynamics basically says that nature loves a mirror. If you took a video of an experiment and you swapped every particle for its antiparticle, reflected the whole thing in a mirror, and ran time backward, the laws of physics should still work exactly the same.
So if I have a chunk of normal metal and I shine a light on it, electrons fly off. That's the photoelectric effect. If I had a chunk of antimetal made of positrons and I shine a light on it,
Positrons should fly off in the exact same way. The math says it should be a perfect mirror image. The photon hits, pays the cover charge, and the positron leaves.
but we don't have antimetal solar panels. You can't go to the hardware store and buy a sheet of positronium. Why not?
Because we live in a matter-dominated universe. And matter and antimatter are mortal enemies. They are like fire and ice.
They annihilate.
Instantly, as soon as a positron touches an electron. And remember, electrons are everywhere, in the air, in the walls, in your body. They combine and turn into pure energy, usually 2 gamma-ray photons. Poof, gone.
So trying to do the photoelectric effect with positrons is incredibly difficult because the material itself is trying to commit suicide the moment it touches anything.
It is. But, as Concom points out in the paper, it's not impossible anymore. We've gotten very good at building traps. We use magnetic and electric fields to hold antimatter in a vacuum, suspended so it doesn't touch the walls. We can make antihydrogen. We could even make positronium.
I noticed the paper focuses a lot on positronium. That's not an element on the periodic table, right? It's something weirder.
It is weird. It's an atom-like system. Imagine an electron and a positron orbiting each other, dancing around a center point. It's a doomed romance. They dance for a tiny fraction of a second before they spiral in and annihilate each other. But in that tiny fraction of a second, they exist. They are a bound system. And we can hit them with lasers.
And that is the setup for Kongha's work. He's saying, okay, we can trap these things now. We can hit them with light. We need an equation that actually describes what happens. Because Einstein's old simple addition isn't going to cut it in this chaotic environment.
Exactly. He's renovating the house Einstein built. He's keeping the foundation, the conservation of energy, but he's adding a new wing to deal with the chaos of antimatter.
Let's walk through this new equation. I'm looking at it in the paper, and it's definitely more cluttered than the original. It starts the same way. You have the incoming photon energy, Achu, and you have the output, the kinetic energy of the positron flying away.
Right. Input and output, that hasn't changed. And you also have the positronic work function denoted as Phi plus.
Which is the cover charge again.
Yes. It's the energy cost to rip that positron out of whatever magnetic trap or bound state it's currently sitting in. If the photon doesn't have that energy, the positron stays trapped. So far, we are still just mirroring Einstein.
But then we get to the corrections. This is where the paper really shines. It stops being simple algebra and starts becoming, real quantum theory. The first big addition is about positronium mining.
Right. This accounts for that doomed romance I mentioned.
Yeah.
If your target is positronium, that electron-positron pair, the positron isn't just sitting there alone, it's holding hands with an electron.
So the photon has to break them up first.
Exactly. You need extra energy to sever that bond before you can even think about kicking the positron out. The paper notes that for the ground state of positronium, this binding energy is about 6.8 electron volts.
Which sounds small, but in atomic physics, that's a significant toll booth.
It's a very specific breakup fee. If you don't account for that, your math will be wrong. You
Yeah.
won't see any positrons. You'll just be heating up the system without releasing anything.
Okay, so that's correction 1, the breakup fee. Now let's look at correction 2. This is the one the author seems most excited about. The CPT factor, or delta CPT.
This is the spicy one. This is the term that makes theoretical physicists lean in closer to the chalkboard. This term is basically a question mark.
A question mark.
In the standard model, the basic rulebook of physics, this term should be 0. It shouldn't exist. The energy required to remove a positron should be identical to the energy required to remove an electron. Symmetry says they are the same.
But Kamha included the variable anyway. He's leaving a placeholder.
He is. He's saying, what if it's not 0? If we run this experiment with extreme precision, and we find that the math doesn't quite add up, that maybe it's a tiny bit harder or easier to kick out a positron than an electron, then this term becomes non-zero.
And if it's non-zero, that means the symmetry is broken. It means the mirror is cracked.
It means the laws of physics are slightly different for antimatter. And that is a huge deal. That's a window into new physics. It implies there is something beyond the standard model. Maybe it connects to string theory or quantum gravity. It's the loose thread that could unravel the whole sweater.
It just blows my mind that a tiny variable in a photoelectric equation could be the thing that breaks the standard model. But let's look at the third and final correction before my brain melts. The annihilation penalty, or -EN.
This one is much more practical. I think of it as the danger tax.
The danger tax, I like that. Because being a positron is risky business.
It is. The paper describes this term as being inversely proportional to time, tau. Basically, the clock is ticking. Unlike an electron in a copper wire, which can just hang out for a billion years, a positron in a trap is surrounded by things that want to kill it. It has a limited lifetime.
So how does that change the energy equation? Is it just about probability?
Essentially, yes. The equation is trying to predict the effective energy of the emitted particles. But if half of your particles get annihilated before they even leave the surface, you are losing energy. The system is leaking energy into gamma rays.
So you have to pay a tax. The denser the electron cloud around you, the higher the tax, because you're more likely to die before you escape.
Exactly. The equation acknowledges that escape isn't guaranteed. You lose efficiency strictly because of the volatile nature of the particle. It's a term Einstein never had to worry about because electrons don't spontaneously explode when they touch other electrons.
So putting it all together, we have this complex new formula. We've got the positronium breakup fee, the potential asymmetry factor, and the danger tax. It's a much more sophisticated beast than what Einstein wrote in 1905. But now comes the so what question. Why do we do this?
Beyond just making the math rigorous.
Yeah. The paper outlines a few implications. What can we actually do with this?
The first big one is what we touched on with the CPT factor, testing the universe. This equation gives experimentalists a target. If they can build a system to measure this photoelectric effect on antimatter, they can hunt for that symmetry violation.
And if they find it,
Yeah.
that connects to the Big Bang problem.
It connects to the biggest problem of all. Why are we here?
Walk us through that logic.
Think about the Big Bang. Our current theories say it should have created equal amounts of matter and antimatter. 50-50. Perfect symmetry. But if matter and antimatter are perfect mirrors of each other, they should have all annihilated each other in the first second of the universe.
It should have been a very short, very bright fireworks show, and then nothing. Just empty space filled with light.
Exactly. But that's not what happened. We are here. Stars are here. Matter won. There had to be an imbalance, a slight asymmetry, something that tipped the scales in favor of matter.
And if this extended photoelectric effect reveals that non-zero CPT factor,
If it shows that light interacts just a tiny bit differently with positrons, that could be the smoking gun. That could explain why matter survived and antimatter didn't. We exist because the mirror was slightly warped.
that is incredible. We're testing the bedrock of existence using a laser beam. But the paper also mentions some applications that feel a bit more, well, Star Trek,
Oh, absolutely. And talks about antimatter spectroscopy.
which is basically X-raying antimatter.
In a sense, spectroscopy is how we figure out what things are made of by analyzing the light they emit or absorb. If we understand exactly how light kicks positrons around, using this new equation, we can use light to probe the internal structure of antihydrogen. We can see inside them in a way we currently can't.
And then there is the confinement angle. The paper talks about artificial lattices.
This is the engineering hurdle. If we want to use antimatter for anything like energy storage or medical imaging, We need to store it densely without it exploding. The paper suggests that if we understand the binding energies, that work function term, we might figure out how to create stable lattices of positrons, essentially an antimetal.
Which naturally leads to the topic of propulsion. I saw the phrase controlled annihilation and my ears perked up.
Of course, that's the dream for interstellar travel. Antimatter is the most energy-dense fuel in the universe. It's 100% efficient mass-to-energy conversion. But you can't just throw it in a combustion engine.
You need a throttle. You can't just let it all blow up at once.
Exactly. And the photoelectric effect is a throttle. Think about the mechanics. You have your fuel, the trapped positrons sitting there, stable in their magnetic trap. When you want thrust, you hit it with a specific frequency of laser.
The laser pays the cover charge.
The laser triggers the photoelectric effect, releasing a stream of positrons. They mix with electrons, annihilate, and boom thrust. You turn off the laser, the positrons stay trapped, the thrust stops.
It gives you precise control over the reaction. It's not just a bomb, it's an engine.
It's the ultimate variable throttle. Now, are we building this tomorrow? No. But Conga has provided the math that says if you build the trap, here's how the engine works.
It really changes how you look at a beam of light. It's not just illumination. It's a tool that can pry apart the fabric of matter and antimatter.
And it serves as a reminder that science is never finished. We tend to think of 1905 as ancient history, that those books are closed. We think we know everything there is to know about the photoelectric effect. But Kange is showing us that there is always another layer to peel back.
He's essentially built a hypothesis generator. He's throwing down the gauntlet to the experimentalists. He's saying, here's the math. Here is what should happen in the mirror world. Go build the machine to prove me wrong.
And that dialogue between theory and experiment is how science advances.
I want to leave everyone with a final thought, something that really stuck with me while reading this. We talked about that mirror world. We usually think of a mirror as a perfect reflection, but what this paper suggests is that if we look closely enough at the reflection, at the way light bounces off that antimatter, we might see the crack that allowed the entire universe to come into being.
That is a profound thought. If the mirror wasn't cracked, we wouldn't be here to look at it.
Something to think about next time you see a solar panel glinting in the sun. It's a descendant of the physics that might explain our very existence. Thanks for joining us on this deep dive into the strange world of positrons.
My pleasure.
Catch you on the next one.